The next thing I need to talk about is convolution. So before we get to how convolutions work with Fourier transforms, I want to describe the process of convolution to you with an animation. So before we get into any maths, I'm just going to give you a picture of what a convolution is, because really, if you understand this picture, the maths becomes almost secondary. So here we have a function in blue, which is a top hat function. It's going to remain stationary. Passing through this blue function is a second top hat function, a little narrower, and it's going to be moving through this top hat function. And at each time step, we're going to find the product of these two functions and then integrate that product. So at the very beginning, there's no overlap, and we have a function which remains 0 here, and I'm plotting that function down here on the bottom graph. At the moment where they start intersecting, we start to have some value here, which is now non-zero. So we're taking the product of these two functions here, which gives us a little top hat function, and integrate it, and it gives us some area. And we plot the area here as a function of the position of that yellow top hat. And as we increase the amount of overlap, then this integral increases until the yellow function is fully within the blue function, and then we have a constant, because now the product of these functions integrated remains constant until it starts to leak out the other side, and then it drops back down again. And so that, on the bottom here, is the convolution of these two functions. If the blue function here is the function f of tau, and this function here is the function g of t minus tau, then this is the convolution, the integral f of tau g t minus tau d tau. Here is a second example. This time we've got the same top hat function back again here in blue, but the function we're integrating with now is this sharp sort of spiky thing. And as we animate this through and integrate, what we'll find is a spike at one edge and a spike at the other edge. And the reason for that is that in the middle here, the area, top and bottom of that yellow function, is the same, and so the integral there goes to 0. But as you pass through this edge here, then you get, for some short amount of time, an integral that is non-zero. And so what you've done actually is detected the edges of this box. So if you've ever heard of an edge detection algorithm, it might look something like this. So let's get a little more formal in defining convolution. The convolution between the functions f and g is defined like this. We use a star to indicate the convolution of f with g, and it's defined using this integral here. The variable over which we're integrating is tau, but after we've integrated over tau from negative to positive infinity, we're left with just a function of time, this variable here. And so to explain what this integral is doing using this animation here, the top plot here shows tau as the x-axis. So it's this function f of tau and g of t minus tau. And here is the variable t, which we're changing. So to calculate the convolution, if you like, we start with some value of t, in this case starting with -2. We calculate the integral, and we write down the value and plot it. Then we change t until we get some action. So here we've got a value of t, it's a negative 1.08. We find the integral and write down the value of that integral and plot it on this graph as a function of time. And you keep changing t, and every time, for every value of t, you do the integral over tau to get some value of the convolution at time t. And you keep doing that until finally you've developed an entire function of t. So it's a really common sort of integral that describes a lot of physical processes, and this one here, for example, would be a running average. So you've got some function in blue, and you can take a running average over some width defined by this yellow function here, and then this function down below would be the running average of this blue function, where you're taking the running average over this box width here. And as I mentioned before, this other process here would be an edge detection algorithm, where you use the convolution with this particular shape here to detect the edges of some shape. So, as I was saying, the value of the convolution for any given t is the integral of the product of the function f of t and g of t, as one of them is time shifted through the other. So the time shifting is done with this variable tau, but the convolution is some function of t, not tau. Now the convolution, defined like this, has quite a neat interaction with the Fourier transform. So the Fourier transform of the convolution of these functions f and g is equal to the product of the transforms. That is, the transform of the convolution is the product of the transforms. And there's also a theorem for going backwards, that is that the Fourier transform of the product of two functions is proportional to the convolution of the two transforms, and there's a factor of 1 on 2 pi out the front. So these two theorems here actually allow us to do a lot of maths in a pretty straightforward sort of way. Sometimes there's a physical process that's a convolution in the time domain that's kind of hard to compute. Sometimes it's really easy to go into the Fourier domain, find a product, which is a simple calculation, and then you can think about doing the inverse transform.